Swayam Prabha. Digital India. Educated India.
Hello and welcome to another lecture on Introduction to Machine Learning. Today we will talk about feature engineering and feature selection. So the learning objectives will be that we will learn to articulate why right features are important and wrong features can be harmful in estimating machine learning models. We will look at ways to generate some new features from existing features and be aware of some common features for common data types such as images and text, and we should be able to apply some feature selection methods. So let's dive in. We will start with some motivating examples of why right features are important and wrong features can be harmful. So let's take the example of a two feature a space of two features. So let's say this is x1 and this is x2, okay, and let's say we are working on a classification problem, and it's possible that all the positive samples are somewhere on a straight line, and then we also have positive samples with large x2 and small x2 value, and then we also have negative samples. Okay. So as you can see that neither of the two features can help us discriminate between the two classes. So if I were to draw some decision boundaries, any decision boundary that is parallel to one of the axes, which means I'm just using a threshold on either x1 or x2, is likely to misclassify, right? So I don't want these axes, but what I can see that there is a clear linear classifier along a diagonal line, along a slanted line. So if I take a different color to show the line, so let's say if I take this line and project all data points onto that, then on that line what we will see is that the features are well separated. So if I project all the features, all the points onto that line, so in that case I will get along that line I will get all the positive samples. I will get all the positive samples on one side and all the negative samples on the other side, so that when I draw a threshold, right, it's possible that I will be able to easily separate a lot of the positive and negative samples. So as you can see that there is a linear combination of two features that may be more important, right. So we looked at this in the context of the classifiers, the linear classifiers. So basically what linear classifiers are doing is when you have w1 times x1 plus w2 times x2, etc., we are trying to find an oriented hyperplane in the n dimensional space, where on that hyperplane we are able to separate the positive and negative samples, okay. Or we are finding a line on which we can separate the positive and negative samples. So that's one example. The other example could be that we have x1 and x2 space, right, and in which everything can be separated along only one of the features. So let's say only along x1 feature, and along the x2 feature we don't get much separation, but because x2 is also in the mix, the classification boundary that we will get might be a little bit slanted. That means it takes into account x2. It's not the classification boundary is not parallel to the x2 axis. So in that case x2 can be thought of as a confounder, and sometimes it can lead to classification results that are not very good. So in such cases, if we eliminate x2 feature, it might actually lead to a more robust classifier when we are looking at test samples that are not from this training subset. So in general, if we look at a graph of number of features, and we look at accuracy or some performance metric, what we find is that if we have very few features, obviously we won't have good accuracy because we haven't captured all the information, but very soon the accuracy tops off and then it even starts to go down slightly. And the reason it starts to go down slightly is because the extra features sometimes act as confounders. Now if I have an optimal number of features, here I still have the problem of finding what is that optimal subset. So your feature selection is about finding that optimal subset. We will come to that in a bit, but these examples should serve as a motivation for why we need feature elimination. Now similarly, we also need to generate new features sometimes, because in the given set of features the problem may not be easy, but by generating new features the problem can become easier. So let us take the example of an XOR problem where all your positive samples are here, right, in the first and the third quadrant, whereas in your other quadrants we have the negative features. So here it is x1 and x2 space. Now if I am able to generate a third composite feature which is x3, right, so x3 is, let us say, x1 times x2, so this is x1, this is x2, this is x3, then what will happen is that all the positive samples will also be elevated, although they will be in opposite quadrants, but they will be elevated, and all the negative samples will be below on the negative side of the x3 line, so that when I have a plane which is a threshold that is parallel to the x1 x2 plane, then that hyperplane can separate the positive and negative examples. So here I have introduced a feature x3 is equal to x1 times x2. So with a new feature I am able to separate the points better. Another example is that, let us say, if we had all the positive points concentrated closer to the origin and negative points that are away from the origin, then I can introduce another variable x3 which is x1 square plus x2 square. So then I will basically introduce this variable x3 where all the points will be in the lower values of, all the positive points will be in the lower values of x3 and all the negative points will be on the higher value of x3, and then I can again use a hyperplane linear classifier to classify between the positive and negative samples. So all these point to a careful selection of features, a careful crafting of features, and having the domain knowledge to figure out which features are likely to discriminate between different classes or are likely to give you good regression results. So now let us dive in with some more examples. So some specific feature transformations that we can start with, the simplest ones that take one feature at a time into account are these straightforward univariate transformations such as power of x, log of x, and exponential of x. So basically what these are doing is, now let us say this is your original variable x and this is my, so let us call it x hat, this is my transform variable x hat, right. So there is a mapping between the two. If I take x to the power p, then I can get different kinds of curves for different values of p. So for example, if p is greater than 1, then, and let us assume that all of these are all the x's lie in the positive range, x belongs to, let us say x belongs to r plus, then I can have something like this when p is greater than 1, and I can get something like this when p is less than 1. Okay. So what I am doing is I am taking a larger range of x and mapping it onto a smaller range of x for p greater than 1, and I am doing the opposite when I am using p when I am using p less than 1. Okay. And I will show you in a bit what that actually accomplishes, but let us first look at some other ones. Another popular transformation is a log transformation, and basically what we are doing in log transformation is, if you have x here and x hat here, it's basically another monotonic transformation, that is mapping an exponential distribution into an exponential variable. It is compressing it into a linear range. On the other hand, the exponential transformation is doing something opposite, where if this is x hat and this is x, it is doing the opposite of what log is doing. Right. So now let us look at why we do these transformations. So essentially what we are thinking is that there are certain distributions of random variables that are easier to deal with. For example, Gaussian distribution or normal distribution or uniform distribution. So these are easier to deal with because they are better understood. But what if your input data distribution is not the same as one of the desired distributions? So in that case, we would like to come up with a transformation that roughly converts or transforms a variable into a better characterized distribution. So let us say if we have x here and we have x hat here, right, and so let us say we are using the log transformation, right. So this is your log transformation. So what we are thinking is that if what our objective is, so objective is x hat should have an easier distribution, easier in analytical sense, right. So what does that mean? So let us say if I were to draw the distribution of x hat and I want that to be a normal distribution, right, whereas x itself may not have that normal distribution. So when will a log transform a variable x into x hat, where x hat has a Gaussian distribution? So basically we will have a exponential of Gaussian distribution, then the log transform will bring it to the Gaussian range, right. So to visualize that, basically your x hat is going to be it will have a very large tail, okay, it will have a very large tail towards the positive side, right. So this side of the tail is much larger, and we want to compress it so that it becomes a Gaussian distribution in x hat. So in general, the way to think about the transformation of distributions is the following, that we have, let us say we have a function f of x, right. So let us say x hat is equal to f of x, right, and we have some distribution p of x. So let us first start with let us first define an inverse distribution. So we assume that x and x hat have a monotonic relationship, so which means that now we can invert it, right. So we will call this f inverse of x hat, okay, that is equal to x. So we will assume that there is an f inverse function that we can find that can take the x hat value and bring it back to x, okay. So now what we will define is the distribution, let us say if the distribution of x is p of x, okay, and the distribution of x hat is q of x hat, then what is the relationship between the two, right. So q of x hat, okay, is going to be a function of, sorry, is going to be the p of this f inverse of x hat, okay, times the derivative with respect to x hat of f inverse x hat. Okay, times mod of derivative with respect to x hat of f inverse of x hat. Okay. So where does this mod of the derivative come? So basically, finally, let's simplify this. This is going to be p of x, okay, times dx by dx hat okay, mod of that. So where does this mod come from? Basically, this entire derivation hinges on looking at cumulative distribution functions. Remember we said that let x hat be a monotonic function of x, but we did not specify whether it is monotonically increasing or monotonically decreasing. So we have to take the two cases into account. The first one will be monotonically increasing, the other will be monotonically decreasing. So what that means is that for the monotonically increasing function, let's just derive that, and for the decreasing function there will be a negative sign, and both can be taken into account together by taking the absolute value of the derivative. So the derivation is quite simple, that your probability that this f of x, okay, is less than equal to x hat, right, is going to be the probability that x is less than equal to f inverse of x hat. Okay. So this is equal to the cumulative distribution of f inverse x hat. So this cumulative distribution is nothing but the integration of the original distribution function. So I'll just call it p of x of f inverse of x hat. So this is just a cumulative distribution function. So anything, so basically if we look at the cumulative distribution functions of x and x hat, both of them go from 0 to 1, right, and but they go from 0 to 1 at different shapes. But there is also a correspondence between every point in x with some point in x hat, right. So the height of those points are going to be the same. Basically that is the matching criteria, because the probability of getting that any value below that value is going to be the same because of the one-to-one relationship between x and x hat. So once we take the derivative of this, we will find that we get two different derivatives for the case when it is monotonically increasing versus monotonically decreasing. Here we assume that it is a monotonically increasing function, that's why the sign did not change. The sign here will flip when we will have a monotonically decreasing relationship. So that's why it leads to the absolute value. So that is an example of why we need to sometimes transform single variables. Another example would be, let's say our distribution of x is such that it is it's of this shape, and we want to convert it into something that is roughly Gaussian, right. So all these large values, if we take the log of that, they will shrink and they will become roughly Gaussian. So that is why we take that log transformation, and the opposite of that is true for taking the exponential transformation. And similar considerations apply for taking value power transformation with p, with the power being greater than 1 or less than 1. Another place where it is essential to have new variables is when one of the actual features that we measure is a discrete variable. So for example, let's say we have a variable which is fruit, right? So for example, let's say we want to predict whether the person is healthy or not, and we analyze what fruit, what kind of fruits they eat on a daily basis, or which is the fruit that they eat most often, and it is one of these four variables. It is either apple or oranges or bananas or grapes, right? And then there are some other variables such as how much of it they eat, and what other things they eat, like protein and carbs and fat and etc. So now with these, so let's say they eat only one of these fruit, then we are given this feature about their food habits in a discrete variable, and that discrete variable can take one of four values. Now these discrete variables are not, they don't lend themselves to mathematics, mathematical analysis or programmatic analysis. So what we do is we convert it into a mathematical variable, and the variable of choice is for n levels. So these are n levels, means we have, for example, 4 different levels of fruit, and we convert it into n minus 1 binary variables. So this is going to be in a way that each variable is either 0 or 1. So it's a binary variable. So this dummy variable, this dummy I belongs to either 0 or 1. Okay, so it's a binary variable, and we don't need n of them because we can encode one of them as all zeros. So that is the base value, right? So and that choice is arbitrary. Apples need not be the base value. We might have as well used oranges as base value or bananas as base value, etc. And for all the other ones, we'll have one hot encoding that that one of the dummy variables will be 1, the others will be 0. Again, one of the dummy variables is 1, the rest is 0. So what will happen in the model is that we will have something along the lines of w times x d1, x dummy 1, w1 times x dummy 1 plus w2 times x dummy 2 and w3 times x dummy 3, right, and plus b. So what happens to the effect of apple? So basically effect of apple will be in the base, in the bias, okay, it will be in b. And what we are saying is that if instead of apples we the person is eating more grapes, or the person is eating mostly oranges, or the person is eating mostly bananas or mostly oranges, then the weights capture the relative change in effect with respect to b, with respect to the base effect b, right. So everything else is with respect to the base attribute, base attribute that we have for that particular feature, okay, the base value that we have for that particular attribute. Okay. So keep that in mind. So whenever you have discrete variables that are not encoded as a number, we need to convert it into number so that we can apply some mathematics to it. Now another type of variable addition is adding interaction variables. I will give you an example here. So let's say we are talking about per capita income of countries, and there are two types of countries that we have that so let's say we are looking at it from the point of view of investment in or let's say percent of tax, right. So tax rate and per capita income. Okay. And let's say we have two different types of countries. We have socialist countries and we have capitalist countries. For both of them, if we increase tax rate, the per capita income, let's say, goes down. Okay. But for just the socialist countries, we have a graph like this, whereas for the capitalist countries, let's say the graph is like this. Nothing about a political statement, just making some graphs. Okay. So one of them is capitalist and let us say the other are socialist. Okay. And let us say these are the graphs that we would get if we were to analyze them separately, but instead if we analyze them together, then what will happen? We will get some sort of an average effect. Okay, so we will get some sort of an average effect. So this is the average. Okay, so what is the average effect? So average effect basically is saying that if we do not include this variable, the type of economy, if we do not include that, then we will get the average effect. Otherwise, if we include the type of economy, then what we will get is we will get two different graphs for the two different countries. One of them will be like this, right, and the other will be exactly parallel to it, but it will be shifted up by a bit. Okay. So this will be the capitalist and this will be the socialist. Okay. So why do we get this kind of an effect? Why are we not able to capture different slopes? Well, the answer lies in the equation itself. So in your equation, your per capita income y, right, is going to be modeled as W1 times tax rate plus W2 times the type of economy, which is 0 or 1, right, plus B. Right. Your type of economy is what? Your type of economy is either socialist or capitalist. Right. So because of that, now if you think about this, these two together act as variable biases. They do not change the slope. They do not change the slope with respect to x. If I want to change the slope, then I will model it differently. Then I will model it as W1 x1, okay, plus W2 x2 plus W3. Now I will have x1 times x2 and then I will have B. So now I have this term where I have the multiplication of x1 and x2. If I use that, then I am able to model this kind of a graph, right, because now for different x1s I will be able to get two different slopes. Okay. Whereas in the first case I am not able to get two different slopes. I will get the same slope for x1. In the second case, W3 x2 is modifying the slope with respect to x1. Okay. So if I know that there is interaction between two different terms, what I mean by interaction is that their combination is important, right. It is not a single variable that can capture an effect by holding the other variable constant. Their interaction is important. Then I need an interaction term, which is usually a product of two different terms. We saw this earlier in the case of the XOR problem, where all the positive cases were either in the positive quadrant or the negative quadrant. So we introduced a multiplicative variable that basically elevated all of them above the third composite variable for the positive range of the composite variable. So it's a similar, that was basically the interaction variable, but there are other reasons that even in regression, especially with mixed variables where you have discrete and continuous variables together, interaction terms can be important, but that makes the model a little bit unstable in the sense that you get a lot of correlated variables. So this x1 x2 variable now is highly correlated to both x2 and x1, so that makes the solvers a little bit unstable. Okay. So we already saw how to insert interaction variables. So let's say if we have variable xi and xj, we can insert variables which are xi times xj, right. So that is how we will insert it. The caution that I was talking about was that now these will be correlated to both xi and xj, and the problem with that is, let's say if two variables are completely correlated. So let's say we have x1 and x2 are completely correlated, and x1 has weight w1 and this one has weight w2. So let's say x1 is equal to x2, right. So this model is exactly the same as x1 plus alpha, sorry, w1 plus alpha, and so here w2 could be any weight minus alpha, right. So these two models are exactly the same, so there is an ambiguity between these two models. So if there is a strong correlation between two variables, here there is perfect correlation, but let's say even if there is strong correlation, not a perfect correlation, we can trade off one coefficient, one weight for another, and we will still have roughly the same predictive answer, and that's what creates ambiguity. So whenever we are inserting interaction variables, we have to be cognizant of this, that these are going to be correlated with the original variables that were used to create the interaction variables. And the other thing that will happen is you will have more variables, and potentially you can have more variables than unknowns, or more variables than the number of samples, which can also lead to ambiguity in solutions. So all this requires variable elimination, it requires regularization of models, so that you can get better machine learning models. Okay, we'll come to variable elimination in a little bit. Let's first talk about image features. So these are, why image features? Because some of the very useful data that you can deal with are these few types of data. One is images, right? Because we take a lot of images for different scenarios. We take images not just in consumer photography, but also for a lot of industrial applications, a lot of service applications, and so forth. And so for example, face images, traffic images, images of materials that are, or components that are being produced in an assembly line, and so forth. The other important variable types are audio and text, and video is a combination of some of these, right? So these are some of the important variable types, in addition to the vector type data that we have already been talking about. So if we have images or audio or text, we need a way to convert them into vectors, and that is basically the job of finding features from images. And then once we have extracted those features, we can put those features into the machine learning models that we've been talking about, and we can do classification and regression based on that. But this feature extraction requires domain knowledge, right? So you have an image. What is an image? Image is going to be a two-dimensional array of pixels, and possibly with a third dimension which codes the color R, G, and B. And this is going to be a very large array. So let's say an image could be of size 1 megapixel, image could be of size 1000 by 1000, right? So it has 1 million, roughly 1 million pixel values, and that's a very large set of dimensions for a single data. This is one sample. Similarly, you can have a second image that is also 1000 by 1000, right? So if you have only 10,000 images and each of them is 1 million in dimension, because it has 1 million pixels, that's a lot of data to deal with. So what we need to do is we need to take this image and boil it down to, let's say, 15 numbers. So you have 10,000 samples and 15 dimensions per sample. So what are those 15 numbers? Well, we cannot arbitrarily just subsample some pixels. We cannot just average the pixels. I mean, we can, but we need some more intelligent features that is based on domain knowledge of what are the underlying characteristics of images that are useful for recognition tasks or for classification tasks, etc. So let's look at what those features might be, and this is goes into a different kind of a course, which is image processing. So we will not go in detail into that course behind the motivations for these features. I will just list them so that you are cognizant of the need for finding good features based on your understanding of images. The first basic type of feature is that you take all these pixels that you have and we form an intensity histogram. So this is the intensity of a pixel. What is intensity? Intensity is the gray level. So if it is 0 intensity, it is black. If it is highest intensity, which is usually 255 for an 8-bit coded pixel, then it is white. So then what we can get is from 0 to 255, if we treat it as a continuous range, we will get some sort of a distribution, right, of pixels. And darker images will be shifted towards the left, brighter images will be shifted towards the right. Images with low contrast will have a narrow range, images with high contrast will have a broader range. Okay. So these all, let's say, end at 255, 0 to 255. So based on that, we can use the histogram or some summarization of the histogram itself as a feature, right. So we can divide this histogram into bins, and we can say that, okay, I will divide it into 10 bins of range 25 intensity levels each, and whatever is the area in one bin, that will be feature number x1. Okay, similarly I will have feature number x10. Okay, so the 10th feature for a 10 bin histogram. So now all the images that are darker will have x1, x2, x3 as large values, whereas those that are brighter will have x8, 9 and 10 as large values, right. So here I also assume that I have normalized this histogram, so that I have divided each bin by the total number of pixels in the image, so that they all add up to 1 and it's normalized. It doesn't depend on the size of the image. So because images come in different size, sometimes the size invariance of features is important, and we do that using something like this. Another way to describe this histogram would be to describe different statistical distributions of the histogram. So for example, I can say that I will describe the mean intensity, I will describe the variance of the intensity, I will describe the third central moment of the intensity and so forth, which is the skew, and then kurtosis, which is the fourth central moment, and so forth. So I can also do that, and then these becomes my x1, x2 and x3, etc. So these could be the new features. Things become more interesting when we are talking about color images, because in color images you have red pixels, you have green pixels, and you have blue pixels, right. So basically, even if we take all the 0 to 255 ranges, we actually have bin values that will be in a cube, right. So what we can do is we can say that we will have 256 to the power 3 different features, and we can count each and every combination of RGB values as one feature within the pixel. So that would be a true color histogram, but usually we actually summarize it even further. Usually we do things such as we assume that different brightness of the same hue is the same color, or different saturations of the same hue is the same color. So what is hue? So basically, if you take the RGB values of a pixel, right, so we can assume that R plus G plus B is the brightness, right, or the average of R, G and B is the brightness, and then if all of them are equal, then the color is not saturated. If one of them is much lower than the other two, one is much lower than or let's say the max of the 3 is much larger than the min of the 3 colors, then it is a saturated color. So these ideas can be used to develop color histograms that basically find which colors are more dominant in an image. And I will not go into the details, but whenever you are dealing with images, that is one of the features that you can select. Then just raw colors and raw intensity values are not important in images, are not the only thing that is important in images. Many times it's the texture that is important. So for example, if you have an image of a zebra, right, so then these stripes are important, right. Or if you have image of a particular butterfly, then let's say some other pattern is important. So these patterns are described by something called these patterns are called texture. In real life, texture means when you feel something, whether it is rough or smooth, that is texture. In images, it is basically the self-repeating patterns that are called texture. So to describe texture, we use something along the lines of we either use Fourier descriptors. So basically we take a two-dimensional Fourier transform of the image, and if there is a particular repeating pattern, we will see a spatial frequency will have a large power value, and that will give us some idea of what the texture in the image is like. So we can use Fourier descriptors, or we can use something along the lines of a GLCM, gray level co-occurrence matrix, GLCM, gray level co-occurrence matrix. So what that means is we will take the gray levels. So let's say we just have 4 gray levels. We have binned the image into 4 different gray levels, 0, 1, 2 and 3. So we have 0, 1, 2 and 3, and then we have 0, 1, 2 and 3. So we make a 2 by 2 matrix, a two-dimensional matrix, where each row represents every gray level and each column also represents every gray level. And whenever we have 2 pixels that are together and they are both 0, then we will increment this by 1. If we have 2 pixels where one is 0 and the other is 1, we will increment this by 1 and so forth. Okay. So we will increment different bins of the GLCM matrix based on the which pixels appear together in the image. And if you have, for example, zebra where white and black are appearing together, you will see that the 0, 3, which is white is going to be 3 in this case, and is going to be 3, yes, and black is going to be 0. You will see that you will have a lot of these two values that will pop up. So that will capture a very stark contrast type of a texture, and then you can extract, you can use the bins of this GLCM matrix itself as features, or you can use different summarizations of this GLCM matrix as features and so forth. So that's how we can extract texture from images. Then we also want to extract shapes from images, and for shapes, let's say most of the image is dark background and we have objects that are light in foreground, right, and we want to extract the shapes. Now you can see that the one problem that immediately occurs with images is that the same shape can actually be smaller in a smaller image, okay, or it can be far away from the camera, so it's not smaller but it appears smaller, but it's actually the same shape, all right, or it can be rotated, or it can be translated left, right, up or down. So we want features that describe shape that we might want them to be invariant to these transformations depending on the application. So there is something called hue invariant moments, that basically extract these features that are that capture the shape, but they are invariant to the size scaling or the translation or the rotation. So what are invariant moments? So as we all know, there are moments which are basically statistical descriptors. So for example, we can compute the average, the first moment, which is mu ij. We can take it as a sum over all x positions and all y positions of pixels on images, and we can take x minus the central x, okay, and y minus the central y, okay, times the intensity of that at that particular location. So we can treat the intensity as some sort of a probability density, right, some sort of a weighting factor, and based on that we can see where the average intensity of the image lies. And now what we can do is we can actually, so sorry, I forgot the powers here. So this is x minus, there's no, yeah, this is going to be power I and power j. So when I and j are 1, then basically we are looking at the first moment. So similarly we can have different powers and they will give you the second moment and so forth. and when you subtract the first moment from the second moment, you start to get central tendencies. So there is a whole bunch of formulas for 7 different invariant moments, Hu invariant moments, that can be used for calculating shape features. So similarly, there are other features which take into account both texture and shape, and those are wavelet features. So a lot of these you can find in other courses, but just be aware of what are some useful features that can be extracted from different specialized types of data such as images. Now keeping with the same theme, let's talk about audio features. So what is audio? Audio is basically, you have a time axis and then you have a pressure waveform. So this pressure waveform usually is sampled at 20 kilohertz or 40 kilohertz, right? Why? Because that is the limit of frequencies that a human ear can reliably hear. After that it becomes ultrasound, and which is something that we don't hear, but other animals can, such as bats that use it for navigation, or we use it for specialized applications such as medical imaging. Now so if we sample this audio signal, basically we get a lot of samples, and the other problem with this is that we don't know about different audio samples how long they will be. So for example, let's say if we are doing automatic speech recognition or automatic emotion recognition in speech, then whether someone will take long time to speak a particular sentence or a short time, we don't know. It depends on the person, and it also depends on when they speak. If they repeat the same sentence, it could be of a different time. So we want to extract features that are meaningful for audio, and yet they are useful for the task at hand. And what has been observed by a lot of research into sound is that the frequency component, the power in different frequency bands of an audio signal is important. So what that means is that we take the raw signal and we take its Fourier transform, okay, and then Fourier transform will basically tell us what is the low level frequency, what is the mid level frequency, and what is the high level frequency, what is the relative contribution of each of these frequencies in this particular wave. So if I take different sinusoids with different weighing factors and I combine them, I should be able to get this original waveform back. Alright, and then these sine waves can also shift left and right, which is the change in phase, and many times in applications when we are extracting features we ignore the phase, but that's another whole topic that I don't want to get into, because phase itself can be important and there are better ways of extracting features where phase is also given due consideration, but most of the time we are happy with looking at just the absolute value of the contribution of each frequency, so which is the power spectrum density. And now what we can see is that different windows in this particular time signal can have different frequency components. So for example, if someone is singing and they are singing a different portion of the song, they might be hitting some high notes, whereas in another portion of the song they may be actually working with low notes. So a Fourier transform by itself is not that useful. We do some kind of a windowing. So we look at different time windows and we do the Fourier transform of each of these windows separately. So so what I'm getting at is there is something called Mel frequency Cepstrum coefficients, MFCC, Mel frequency Cepstrum coefficients, which is one of the default features that are extracted from audio waveforms. And the algorithm, in a very quick way, without getting into a speech processing type of a course, is the following. Basically we will first do windowing, which means for the pressure waveform we will look at different overlapping windows in time. Okay, so this window is only looking at this portion of the signal, the next window is looking at the next portion of the signal, and so we will look at several overlapping windows of the same signal. And for each window what we will do is we will compute the discrete Fourier transform. Okay, and once we have the discrete Fourier transform, From that we will get the power spectrum density, which means what is the power contribution by each of those frequency bands. Then we will basically do something called a filter bank with log energy bank, BANK, and log energy. We will find the log energy. So what that means is that once we are looking at different frequencies now, not time but frequency, right? So the frequencies can range from 0 to let's say 20 kilohertz. We will have these different overlapping bands, but the size of the bands will keep expanding as we go, right? Because when you are in higher frequencies, the change in frequency has to be large for it to matter. When you are in lower frequency, the change in frequency has to be small to matter. So when we pool different frequencies together, we have some central frequency, and we also take contribution from neighboring frequencies, but that neighborhood is large when your central frequency is large. So we use such a filter bank, and based on that we get the contribution of different frequency bands, and then we compute something called discrete cosine transform, and that's how we will get the MFCC coefficients. Another useful feature of that can be extracted from audio is something called spectrogram. So we have time on one axis, and we have frequency on the other axis, and we basically have a two-dimensional array, right? So basically in a particular time window, so if I look at a particular time window, what are different frequency band, the energy contributions of different frequency bands, that's what it captures, and that can be used as a feature provided that the number of time windows is fixed for different samples, and the number of frequency bands is also fixed for different audio samples. So these are some ways to extract features from audio, and some features to extract from text are the following. So let's say we are now looking at natural language text. So let's take an example of a text. The cat was chasing the rat. Okay, so let's say this is a sentence, and I want to extract different things from it. So I want to, let's say, classify this into positive or a negative emotion. So maybe let's take something less neutral than this. I got lucky in the test today, right? So this is LUCKY, lucky in the test today. So this is definitely a positive emotion, and let's say we want to extract, we want to classify this into a positive or a negative emotion. And let's take another example. I was not very lucky today. Okay, so this is another person using the same word lucky, but that this person is expressing a negative emotion. So some common text features that we can extract are, the first one is just a histogram of words. So what I mean by that is, let's say we have a dictionary, and in the dictionary we have, we can start with a and the, but a and the usually don't matter because they are in every sentence and they don't really help you figure out the emotion of the sentence. But let's say I have starting from a and then some other word and whatever, and then I have I, and then I have somewhere I have got, EFGHI, no, got will be before I, so got, and then I have I, etc., etc. So I have a dictionary, and for each sentence I will put a number in the dictionary that here I had one, here I had one, and then for in I had one, and etc. So now I have a feature vector which is mostly zeros, and some places it has ones that encode the words that appeared in that particular sentence. And if we are classifying paragraphs, then we may have more than one, this one may become two, and so forth. and if we want to normalize it by the size of the sentence or the size of the document, we will divide it by all the number of words, and then it will be some fractional value such that the entire vector, all the components add up to 1, but each component itself is between 0 and 1. So that would be one way to encode features, which is basically just the frequency of the vocabulary that you have. So that is usually a good feature to start with, and then we can train classifiers on that. Now those classifiers, if we have a binary classifier for positive emotion versus negative emotion for sentiment analysis, that might be able to figure out that if these two appear together, then it's a negative emotion. If this appears by itself, then it is a positive emotion. We may or may not be able to get it. Now one problem with this is that we are putting an emphasis on all the words together, right? We are not using, making an adjustment for common words that are less informative because they appear everywhere, right? So for that there is a slight variation of this frequency, term frequency histogram, and that is called TF-IDF. So TF is what I just described, which is term frequency. And this is inverse document frequency. That means basically it encodes whether this term differentially appears in this particular document as opposed to other documents. By document I mean the sample, which could be a paragraph or a sentence or a complete document, but whatever is the sample. Document means sample. So does this term appear differentially in this document and or in a few documents, and because of that its appearance is important. If it appears in too many of them, then it is not important. So let's look at this carefully. What is your TF? TF is based on the term and the document. Okay, TF is a function of term and the document. It is the frequency with which the term appears in the document, okay, divided by sum over all the terms tau that belong to this document. Okay. Basically it's a normalized count of the term in this particular document. But now we want to temper this for those terms that appear in lots of documents, and that's why they are not important. Okay. The terms that rarely appear, they are more important. So for that we will also define IDF. Okay. Here we will look at not just the term T, but we will look at entire set of documents, capital D, not small d, capital D. Capital D is a collection of small d's. So we call this corpus of documents. Okay. And here we will have log, okay, of the total number of documents in the corpus divided by 1 plus, okay, the documents in which these terms this term appears, D belonging to D such that T belongs to D. Okay. So the total number of documents divided by the number of documents in which this term, only this term appears, or this term appears, right. So here the numerator, when it is small, you will get a large value. If the numerator is large, then you will get a small value, right. So that will temper the IDF. So basically your entire feature for one term will be TF times IDF. Okay. So this is one popular feature that is used for text. Another way to use features, to get features, is to use pre-trained deep neural networks. In this course we will unfortunately not be able to cover a lot of deep neural networks, but the concepts of machine learning is still important with pre-trained deep neural networks and with deep neural networks themselves. So what you can do is, let's say you have an image, right, you can send it to a very deep neural network. I will call it CNN. Okay. So it takes the input in form of that 2-dimensional matrix of pixels, but the output that it gives is a 1-dimensional vector, and let's say the dimension of this vector is 512 cross 1. Now the weights of this neural network or the coefficients of the neural network are fixed because it is pre-trained on a very large set of images, and it is trained in such a way that these 512 numbers that we have extracted from a very large image are meaningful. They are somehow representing things that are of importance in the image. We assume that we are not going to change the neural network, but now we can take these 512 features for different images, and you can use them in different classifiers, like a logistic regression classifier, in a support vector machine, in a perceptron, or in a decision tree, and we can classify images based on just these extracted features. We can do the same thing with text, where we can take a large pre-trained neural network for text such as GPT-3 and use that, the features that are extracted from that, summarize those features for the entire sentence and use that for something like sentiment classification and so forth. So the theme that we are looking at is that there are various different domain specific ways of extracting features, features that are based on prior knowledge about interaction between variables or how the variables are entangled together and so forth. So when we introduce these new features, we usually have a lot of features together, right? So we have sometimes more features than we can deal with, because a lot of these features could be confounders or they could be correlated and so forth. So reducing the number of features becomes important, and that is the topic of the rest of the lecture. So there are different ways of reducing features. They can broadly be categorized into filter based methods, wrapper based method, and embedding based methods. So what is filter based method? We take one feature at a time and determine its utility, and once we know whether it is useful or not, we will discard it or keep it, and then we will, if we have kept it, we will take all the kept features and we will train the machine learning classifier based on that. So in a first, let's take a step back, right? So let's say you have features x1 all the way up to x100. You have a lot of features, right? And then your samples are from x11 all the way up to x1000, 1 all the way up to x1000, 100. Okay, so you have 1000 different samples and you have 100 different dimensions. Okay, so let's say this is your data set, right? So what is feature reduction in a nutshell is to find subsets, which is basically find these columns, the best subset that is suited for the problem. Okay, so it is basically a best subset selection, best subset of features. Now how many subsets there are? We have 2 to the power 100 subsets, right? Any feature can be in the subset or not be in the subset. So 2 to the power 100 subsets is a lot of subsets. So how do we decide which subset is the best? We are not going to test each and every subset. If we test each and every subset, it can be computationally very infeasible. So what a filter based method does is that it doesn't look at 2 features together or 3 features together, it just looks at 1 feature at a time. Okay, so basically what it does, filter based method, is for each feature okay, decide, keep versus discard. Okay, and then once we have done that, then train an ML model, train ML with kept features. Okay, what wrapper would do is wrapper would generate several subsets. So for some number of features, for some number of subsets, some n subsets, generate subset, Okay, uh, train and test, train and validate ML model on the subset. Okay, on the subset, and basically compare which one is the best. Embedded models are embedded methods are those where the model training and feature selection is happening tightly together as a part of a single process. So example would be lasso, L1 regularization for linear regression or logistic regression. So this is where uh, subset selection and ML are integrated. Okay, so these are roughly 3 different ways of looking at features. Let's look at each of these in little more detail. So before we get into using a large set of features, it's always a good idea to eliminate some features that are highly correlated with other features. Which one of the two to pick, that is a matter of subjectivity, or we can have some sort of a utility metric to find out which I will talk about in a little bit. So but keep that in mind that if I plot the correlation matrix of features, so let's say this is feature x1 to x100, and this is also x1 to x100, and I take the absolute value of the correlations, because strong negative and strong positive correlations both are to be considered as high correlations. So obviously the diagonal will have high correlations because we are correlating with itself, but you can see that you will see these block structures where the features are correlated with each other. Sometimes these blocks appear not around the diagonal but far away. So what this means is that there is a group of features that are similar to each other, and I can permute this matrix. So if I move some rows up, I also have to move the same columns left. So I can permute the order of the features so that these high correlations actually appear as blocks around the diagonal. So each of those blocks, depending on some subjective criteria, that if they are above, the correlations are above a certain threshold, those can basically say give an indication that all but one of the features in this block can be eliminated, okay, and that can lead to feature reduction. So there is a correlation based clustering methods that are available to reduce features, but what threshold to use, that is subjective. Whether we use a 0.9 threshold or a 0.8 threshold, that is subjective, depending on how much reduction we want. And then which of the features to keep as a representative of all the features that are correlated in that block, that is also something that we can play with. So we can look at the individual utility of the features, which I will talk about next. So utility of the features can be, if you look at one feature at a time, can be based on how they are related to different to the predicted, the variable to be predicted, the target variable. So in regression we have ti, right, we have t, and then let's say we have x1 through xd. If I take the correlation of t with x1, with x2, with x3 and with xd, and take the absolute value of that correlation, that might give me an indication of which of these xi's is useful. So the ones that are highly correlated are most likely to actually give us a good answer, are going to give us a good subset for predicting the values of t. Okay, so because we are going to estimate t as w1 times x1, w2 times x2, etc., etc. So the ones that are highly correlated, they are more likely to be useful in the regression model. So that is one thinking. Obviously this does not take into account non-linear relationships. This is only based on linear relationships. It does not take into account interaction between xi and xj. It does not take into account when xi and xj together are more predictive or are perfectly predictive, but than let's say xk or something like that. So it doesn't help us with looking at like subsets of size greater than 1. So it's a filter based method. So that is how we will do it in regression. In classification we can do a t-test. in t test what we are saying is that let's say your t belongs to two values, right? So t belongs to either 0 or 1 or -1 and +1. So that is your two class classification, and for one of them x is so if I am looking at x for t is equal to -1, it is distributed like this, and let's say for x is equal to +1 it is distributed like this. So this is for t is equal to 1. Now this is for xi. For different xi's, for different values of I will have these two distributions will have different overlaps, right? So I want to select those that have least overlap in a relative sense, so relative to their own individual variances. For that there is something called a t-test, which assumes first of all that these variables are distributed in a Gaussian manner. It works only if you assume that they are distributed as Gaussian variables, and then basically there is a formula for that. We will take let's say the mean, so if I take x, some variable x, and I am taking its whenever t is 1 I can take its mean, okay, and then I can take all x's when t is -1. I will take the difference of the two, that tells me how far apart these two are, right? Or let us just call it mu1 and mu2, mu1 and mu -1, that will be easy. So I will take mu1 minus mu -1, right, and I will divide it by, I also want to look at the individual variances of the two. So I will also look at this sigma 1 square by n1, which is the number of samples in when t is equal to 1, okay, plus sigma -1 square n -1, right. So you can look up these t-test, the exact definition of the t-test in standard reference manuals, and basically what that is saying is that not only is the difference important, and I can take the mod of this, not only is the difference important, but I also want to divide it by the individual widths of the Gaussians, because if the Gaussians are too broad, then the difference, a small difference, a particular constant difference does not matter. Only if the variances are narrow, only then a constant difference between the means matters, right. So the variables that give you high t values are more likely to help you with the classification. The variables or the features that are giving you low t value are not likely to help you with the classification. Then there are other ways of finding it, such as AIC and BIC, Kai-K information criteria and Bayesian information criteria, that look at the likelihood of the data that you have predicted, of the model that you have, of the data being generated from that model, and then it also penalizes for the number of variables that you have included in the model. So a way to circumvent a lot of these criteria is to actually have a validation test and see which subset works best on the validation test, or do cross validation. There are other greedy methods that look at different ways of selecting features, such as forward selection and backward elimination. So the way forward selection would work is, we assume that first of all we have no variables in a subset of variables that we are selecting, and we will add variables one by one until some accuracy level has been reached, or a number of variables, that maximum number of variables that we want to include has reached. So let's say we have x1 through x100, we have 100 different variables, right, and initially we say that your subset is empty, okay, there is no variable in it, okay. So then for I is equal to 1 to n, which is let's say less than equal to 100, what we will do is we will measure the marginal utility. Sorry, we will have another loop in here. So let's say your selected subset is phi, and your reserve subset is x1 through x10, x100. So this one has all of these. Sorry, it's a set. Okay. So what we are going to say is that for j in or xj, let's say xj in R in the reserve subset, measure the marginal utility of xj being included in the machine learning model. Okay. So once we have done that, then what we will do is include xk with the largest marginal utility into S and take it out of R. Okay. So basically we are moving one by one variables from R to S, and each time we are finding the one that has the largest marginal utility and we are moving it to S. And backward elimination works the opposite, where S starts with all the variables and R starts with no variable, and we eliminate the ones that has the least marginal utility of if it is eliminated from the machine learning model. So now the disadvantage of these methods is that they look at, if you look at forward selection, let's say we are looking at a variable xi, and xi by itself is not very useful unless it is interpreted with xj, and xi and xj together are very useful, but we will not be able to find that when we reach xi if xj is not already in the selected subset S. Okay. So that actually is one of the disadvantages, and in backward elimination you are starting with a very large model and then you are trying to reduce variables, which can lead to instabilities because there could be a lot of correlated variables already in S, because we start with S having all the variables, and because of that the elimination process may not be very useful. So both of these are greedy methods and they have their disadvantages, but they can work in some cases. And finally, let's look at some tightly linked models, where the embedded models, we already know what is lasso. So in lasso, basically now we are looking at W1 and W2 space. Let's say there are two variables, right? And if we didn't have any penalty, if we were just minimizing, let's say, mean square error in regression, we may get contours of mean square error that look elliptical like this. And when we put another term in the optimization, which is minimizing some constant times the L1 norm of weights, we will get these 45-degree tilted squares for different values of the penalization, right? Then what happens is that for certain values of certain combination of that penalty, we will have these contours that will graze tangentially to this tip, the corner of one of the squares, and because of that we will have elimination of that variable, and this story can unfold in large dimensions also. So basically if we are looking at that penalty, right, so basically we have error term. Okay, so your loss of weights is equal to some error based on the weights plus lambda times L1 norm of W, right. So if I look at no lambda, then basically I have zero error. If I have large lambda, then I have basically weights are zero. So if I plot 1 over lambda, right, or log of 1 over lambda or 1 over lambda, and I look at the mod of the weights of single weight at a time, right. So for no lambda I will have large weights, and as I keep increasing lambda, the weights will decrease and some weights will become 0. Okay, some weights will become 0 earlier, some weights will become 0 later, right, and but eventually all of them will become 0. So depending on different values of lambda, I will have different surviving weights, right, and those surviving weights will be the ones for which the features have not been eliminated. Okay, so in lasso, by changing lambda, I can do both estimating the ML model, which is a whatever is in EW, which could be a linear regression model or a logistic regression model depending on the problem, but I can also do subset selection, and same thing I can do with something called elastic net. In elastic net, we will have a second term, right, and that second term would be, let's say, lambda 2 times the L2 norm of W. And what that does is it actually has a certain desirable property where it will keep correlated variables either in or out of the model together. So let me give you a motivating example. So let's say we have two variables x1 and x2 and they are exactly the same, right, and ideally what we would want is we would want w1 x1 plus w2 x2, okay, plus w3, or let's say w1 x1 and w1 x2, I'll tell you why the two are the same, and then w3 x3, etc., right. So because they are exactly the same or they are highly correlated, then I would want their weights to be the same. I wouldn't want one weight to be very high and the other weight to be very low, because then there is an ambiguity. The same effect we can get by having w1 plus alpha times x1 plus w1 minus alpha, now these become w1 w2 in some sense, x2 plus w3 x3. These two models are exactly the same, provided that alpha does not change the sign of w, right. So between these two, right, the L1 norm of both of these sets of weights is exactly the same, but L2 norm is lower for the first model than for the second model. So even if w1 is 0, right, if x1 is eliminated, it should also take x2 with it, because it's actually the same variable or a highly correlated variable. So either both x1 and x2 should be in the model with a non-zero coefficient, or both should be eliminated from the model with 0 coefficient. So that can only be done, so that elimination happens because of L1 penalty, and the behavior that they stay together or their coefficients are equal happens because of L2 penalty. L2 penalty is large for the second model and small for the first model. So if we minimize an additional term, then we will have that grouping behavior, which is called elastic net. Similarly, in SVM, instead of looking at L1, L2 norm on the weights, we can also look at L1 norm on the weights. So what is an SVM penalty? So the regular SVM is an L2 SVM. So you will actually find another terminology where L2 is used for something else. It's used for square of the xi, the slack variables. But basically what you have is mod of W2 square, right? All right. And then you have plus some C times sigma of sigma of 1 minus Ti, right, Yi. And plus, right. So here we are shrinking that L2 norm on W, right. Instead we can have an L1 SVM where we have mod of W, we have the first norm of that, and the second term remains the same, whatever is the hinge loss. So this is your hinge loss. So what this does is that for some penalty, so here you can have lambda and you can get rid of this. So here you can have lambda here. So for some value of lambda, you will have certain values of W, certain dimensions of W to be 0, and that will effectively eliminate those features. Where is W here? W is absorbed in Y here, right. So that is one way of doing it. So that is what I mean by L1 SVM here. In some publications you will see that L1 SVM, they call this particular term to be L1, and when they take the square of the term inside the bracket, they call it L2 SVM. But that's not what I mean. What I mean by L2 SVM is the L2 norm of the penalty on the weights, and here it is going to be L1 norm, which will lead to elimination of some variables. So this is another embedded method, quite similar to the lasso method, but instead of logistic regression, we have the hinge loss. Okay, hinge loss on each of the samples. And the final method that I will talk about for reducing features is principal component analysis. We will reserve the math for a later class when we actually look at unsupervised methods. But basically what it does is, let's say if you have two different variables x1 and x2, right, and they are highly correlated such that we can actually draw a line, and that line contains most of the variance of x1 and x2 taken together, and its normal line has little variance, which can be thought of as noise. Then finding this line, basically some combination, linear combination of x1 and x2 will give you that space, will give you that composite variable that captures the essence of x1 and x2 taken together, right. So basically what we do is we take the covariance matrix of x1 and x2. First we centralize them, we subtract the means from them, we take their covariance matrix, and we try to find the eigenvalues, the eigenvectors corresponding to the highest eigenvalues, and then we reproject the components, the two variables together onto that eigenvector, onto a single eigenvector. So in n dimensions we will use d dimensions, which is less than n, and so that we can reduce the number of variables that we will feed into the machine learning model, although each of those dimensions capture contribution from all the underlying dimensions. Okay, so it's not variable elimination, it's just dimension reduction. So that's why I'm not talking about it now, we will talk about it later. This is just for a relation between these two. So with these feature reduction methods, especially with L1 penalty, elastic net penalty, and there is a more advanced penalty called scarred penalty, you can actually even deal with problems where the number of dimensions is more than the number of samples. So those are called high dimension low sample size problems, and they are very common in bioinformatics, in gene microarrays, where you are looking at 10,000, 20,000 genes, but you have only a few hundreds of patients, and you are trying to classify them into survivors and non-survivors for cancer. Then you will need a lot of variable reduction, and for that you can use some of these techniques. Thank you.